We're now in module 7. Are we halfway? Or is this the halfway mark? I think so. Yeah, 14, a little bit past, right? So today is about classification. It's the second. It's the first of two. The first of two halves. The first one is classification, and next week is going to be regression. Okay, so. Like always, this is my contact info. So yeah, classification. So there are a lot, just every one of these modules, there are so many more elements that we just can't cover in time. So today we're going to cover what I think are like the big two for classification, and that's going to be logistic regression and random forest. And we're going to focus on how do you score them? How do you quantify the strength of your model, right? And that's what we call these error metrics. Okay. So what is classification? All right, so it's basically predicting on categorical outcomes. If your outcome is a continuous variable, that's regression. And if it's a categorical variable, then it's classification, right? And the classification can come in 3 flavors, right? So you can have binary classification. Your outcome is like a, disease or non-disease, like a case control sort of situation. You can imagine that these red diamonds are the, are the cases, and the blue dots are the controls. Oh, sorry about that. I do this every lecture. My mouse is sensitive to switching the slides. I'll try to keep my hand off it. But in the middle here, we have multi-nominal classification. So that's when you have more than one class or outcome or label, whatever you want to, whatever nomenclature you want to use. So yeah, I'm representing that here as like circles, diamonds, and triangles, right? And the final is ordinal classification. So you have categories, right? But there is an order to them. So the most intuitive example is like a rating system. Like you rate your movies 1 star, 2 star, 3 star, right? Here, I don't know what I meant, which is cuter, I guess. I don't know. So your input is I guess these images, and then the outcomes are how many stars, like 3 out of 5, 2 out of 5. So each one needs to be treated in its own way, and we'll cover all of those. Okay, so let's talk about type 1 and type 2 errors. We have to start with statistics. So what I have shown here in the upper right is kind of like a cartoon of a classifier. It doesn't have to be a decision tree like I have here, but point is you have your inputs. These are like, maybe these are patients, and they have who knows how many features associated with them, not just like sex, which is kind of like indicated here, but any number of features. It goes through this machinery, whatever this classifier is, and at the outcome, it's going to make these predictions, right? Some of those predictions are going to be right, and some of them are going to be wrong, right? That's what we're indicating there with the crosses and check marks, right? So how would you then sort of quantify its like ability to, well, get the answer right, right? Or and so for that, we can look at this sort of matrix I have. This is a diagram, but like these 4 cells here are basically what a confusion matrix is. So for binary classification, you can have for each one of these samples, each one of those patients, you can have their actual condition. Are they a positive case or a negative case, right? And in the columns here, we have the predicted value, right? Is it predicted positive or is this person predicted negative? Okay, so the false negative is when when you said that they were, you predicted that they were negative when in fact they were actually, they actually did have the disease, right? And a false positive is the other way around, when they actually don't, but you are saying that you're predicting that they do, right? So this is the classic definition of type 1 and type 2 errors. Pretty much everything is going to be based on that, sort of formalism, okay? So let's imagine now that your classifier is tunable, and they all are, okay? So I've kind of indicated that with this line here. So with the red little like a Gaussian curve here, this signifies those patients who are true cases, true positives. And the blue one here are those patients who are true negatives. They don't have the disease. And your model is it's gonna draw a line somewhere, right? That says on this side of the line, like above this line, I'm gonna predict them as positive. And the ones on this side of the line, I'm gonna predict those as negative. So so you could tabulate the number of samples or patients that you correctly predicted had the disease, that you correctly predicted didn't have the disease, and on the off diagonal your type 1 and type 2 errors. Okay, so let's have a look at what's going on in this figure here. See, the way it's written here, these patients that are on the right side of this line here are going to be predicted positive when they in fact they don't have disease. So these are your false positives, and over here you have your false negatives, right? Every model is tunable, right? So imagine if I slide this line further back, what's going to happen? Well, I'm going to correctly assign more of these positive cases, right? Like this is going to shrink. If I move this line this way to the left, these false negatives are going to shrink. My false positives are going to grow, right? And vice versa. If I move this line to the right, I'm going to increase my false negatives and decrease my false positives. So you see how your type 1 and type 2 errors are it's kind of like a balancing act. Rarely are these two curves so well separated that you can have 100% like 0 false negatives and 0 false positives, right? If that is the case, then it's probably a problem not worth solving, right? The answer is self-evident. What's usually the case is that there's considerable overlap between the true cases and the true controls, right? The negatives and positives. There's overlap along this, whatever your metric is that you're using. Maybe it's their blood glucose if you're trying to diagnose diabetes, or some genetic marker, or what have you, right? So in like a clinical setting, in a diagnostic setting, in biomedicine, we all love to talk about the ROC curve, right? And this is just a graph of your type 1 errors here, your false positives, and then 1 minus your type 2 errors. So 1 minus your false negatives is by definition your true positives. So you can see how it is it's graphically representing the relationship between your model's sensitivity and specificity. Does that make sense? to everyone? So and your model, you could tune your model, right, to move this line anywhere. And when you move when you tune your model, like every realization of this tuning is a point on this curve. So you see how if I move this line to the left, my what's going to happen? My true positives increase. So so the curve, the ball moves this way. If I move the line to the right, the ball goes down. Okay, so what's the big deal? What's the big deal, right? Well, for binary classification, the area under this ROC curve is a good indicator of your model's potential to be, you know, like useful. Does that make sense? That's kind of like an important notion. Has anybody been tripped up already with what's going on here? Okay, so the ROC curve, so this is a unit square. So a diagonal line right here is no good, no better than flipping a coin. And so the AUC, the area of any realistic ROC curve, has a lower bound of about 50%, right? 0.5. And the best ones have like, the curve goes all the way to the top here and all the way straight down. It has an area of 1. So your AUC is going to go be anywhere between 0.5 and 1. If it's less than 0.5, then I don't know, there's like a funny things going on. It probably just means that your definition of case and controller flipped. But in practice, when you make one of these binary classifiers, the usual way we use it is we then look at the components of that model to see how it's making its decision, right? Which variables it's finding important, or what have you, and you use that to you then try to find some relationship between those variables that it finds important. Well, one of the zeroth order tests you do is you calculate the model's AUC, and if it is, for me at least, kind of like a rule of thumb, if that AUC is less than 0.6, if it's between 0.5 and 0.6, then it's really not a good model, right? It has very little potential to be useful. In other words, if it does such a bad job at predicting, then how can you trust anything it says about what it chose to make its decision, right? So before you move on to your like other analysis, when you look at like feature importance, first check if that binary classifier has an AUC that's, well, useful, right? Above 0.6, and it's a rule of thumb, you know. Oh, there's no problem, Serge. It's a rule of thumb, but that's kind of like the zeroth order test. Okay. So let's talk about prevalence. Okay. So prevalence is, well, basically how many cases do you have in your total population, right? And for very rare cases, that number is, well, quite low, right? And so this is also one of the first things you should check when you're building your model, right? What is the prevalence, or sometimes we'll call it, what is the imbalance in your labels or your classes or your outcomes, right? Most models love it if your outcomes are well balanced. You have just as many cases as you do controls. But often we don't have that luxury. Okay, so what can you do? So if I'm in this sort of situation, I can say, well, you know what, I'm actually interested in correctly classifying that minority class. I don't want to miss those positives. Then you would tune your model to sensitivity, right? You would push that ROC curve, or rather the ball on that ROC curve, to the up the curve. If on the other hand, you can say, no, I want to minimize the false positives, right? If it's actually really bad if I say that someone actually is a case and then I go ahead and treat them, that treatment can be quite dangerous. So it's important for me to minimize the number of false positives. Then you tune your model for precision, right? So you can see how your problem at hand will inform what metric you use to quantify the performance of your classifier, right? And you tune accordingly. Okay, so often I see something like this, right? The metric that will be used is accuracy. How many cases did I correctly assign were negatives, and how many cases I correctly assigned were positives, and use that as the error metric. Well, when it's this, the accuracy metric is really poor when you have an imbalance like this. In other words, I can make a predictor. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by 4. So 2 out of 40 patients, right, are cases. I can make a predictor that always predicts negative, and it's going to be right 38 out of 40 times, right? That's pretty high. That's pretty good, right? So yeah, you don't want to use something like accuracy when you have an imbalance. And that's actually almost always. So you almost never use accuracy. So from here on, we're going to talk about all those methods that overcome imbalance. Okay. Okay, so the first one, one of the most popular metrics is the F score, right? Specifically, it's like the F1 score, but we don't need to get into what that is. So I just pulled this figure straight out of Wikipedia, but the F1 score, it balances the metrics for precision and sensitivity. So you see how PPV, that's precision, the positive predictor value, that's another word for precision. So you have precision times TPR. TPR is actually over here. That's your sensitivity. It's a true positive rate sensitivity. So look what it's doing. It's multiplying your predictive and your precision and your sensitivity and dividing it over the sum of the two, right? So you could think of it like equally weighting your precision and your sensitivity. In fact, that's what it does. It's called the harmonic mean of precision recall. Recall is just another word for sensitivity. Both of these, both precision and sensitivity, well, they're the actual elements in the ROC curve, right? So it's going to push that ball to where that slope is the highest. So it's kind of like at the biggest end of that bump of the ROC curve. Does that make sense what I just said? Why is it so good? Well, here what I have is this is like a three-dimensional plot, right? On the x-axis I have precision, and on the y-axis I have recall, the specificity, right? Sensitivity, sorry. And because it's harmonic, this curve it kind of looks like the surface of a ball, right? In other words, it's smooth and it increases what we say monotonically, right? There are no bumps. There's no little hole where you can get stuck, right? So the reason it's so popular is because a lot of methods that basically march along this curve to optimize it will do well because the landscape is rather smooth. And of course, and so the thing to remember is that this metric has a range from 0 to 1. 1 being the highest, the best score, perfect predictor, and 0 means no better than random. Okay, so F-score, that's probably one of the most popular. Another popular one, I find a little bit more informative sometimes, is the Matthews correlation coefficient. Okay, so you'll find it here on this graph. And you can go through the math, but you know, try fishing them out. I don't think that's rather useful to think of it that way. Think of it this way. The Matthews correlation coefficient basically finds, it's a chi-square test. It's computing the correlation between your prediction, your predicted labels, and their actual labels, right? So when both your prediction and the true labels are like, if they're always the same, there's, you know, it has 100% correlation, the value is 1, right? And in the worst case scenario, every time the actual value is like, you know, case, you say the opposite, right? Control. So it has a minimum value of -1. So it has a value from -1 to 1. In practice, this value should be positive, right? In practice, you'll find that the correlation coefficient is somewhere between 0, no better than random, to positive. And you can say something like, you know, something like a correlation of greater than 0.3, right, is somewhat predictive. If they're negative, the reason why I find it more informative is if it's negative, it's telling you about how you're actually assigning your labels. You may be actually doing well. It's just your definition of case and control somewhere have been switched, either intentionally or unintentionally, or sorry, not intentionally, rather because you misunderstood something, right? It can reveal something about the way you're thinking about the data and how it's being categorized. So yeah, so that's pretty much the only ones I'm going to talk about. There's a lot more, but the F1 score and the MCC. So in the future, when we be training these, it'll ask you what metric, what error metric you want to use. Pick one of these two. Okay. The last big one, binary cross entropy. When we get into deep learning, this is like going to be, like, you're going to see this everywhere, but you could use it in this, in our case too. Okay. So let's dive into how this works. Recall this sort of problem, this classification problem, where we have the diamonds and the circles as cases and controls. Imagine that we have some sort of model, right? Here, let's just say it's a linear model. And by linear, I mean it literally draws a line, you know, in the space of your features. It literally draws a line, and that's just going to be your discriminating line. Above that line, let's just say that it predicts the diamonds. And below this line, it predicts the circles, right? Just like we saw, let me scroll back. Just like we saw here in one dimension, right? That's this line, this discriminating line. On this side, it predicts this thing, and on the other side, it predicts the other. Oops. Okay. So we can now then take, we can compute a metric that sort of balances your type 1 errors and type 2 errors in the spirit of what the F1 score was doing, or what the Matthews correlation coefficient was doing, right? And use this, how can I put this? Like a family of error metrics that are based on, have the form P log P, right? These P log P family metrics, and they are basically metrics of information, as Claude Shannon defined it. Or the flip side, entropy, right? In other words, the amount of entropy, kind of like just like it sounds, like the amount of unknowableness versus the amount of information. They're sort of like two halves of the same coin. without getting too much into like thermodynamics, they'll have this form, P log P. So in the future, if ever you see anything that's like, and they're talking about energy or information, and it has a form P log P, you're like, oh, I know, okay, this is just an entropy method. Okay, so let's take a look at how this is set up. So Y here is the actual value of the ith sample, right? So you have n dots, right? N points here, and Y is the actual value of that ith dot. Y hat, that's your predicted value, right? The predicted value of that ith sample. And because the actual value is either a 1 or a 0, right? And your prediction, we're going to assume that what your output of your model is a probability, right? The likelihood that it is a case, right? A 1. This value is in the range between 0 and 1. But by definition, not 0 and not 1. It's somewhere in between, right? Because if it's 0, that this breaks, just like the question we had in the beginning. So this is a finite positive number less than 1. Okay, so what happens? So if it truly is a case 1, then this value is 1, right? And that means it's going to be 1 times whatever this is just whatever this is, right? If it actually was 0, then it doesn't matter what this is, that you just 0 times whatever this is 0, so you don't count it. So what is this doing? This is looking for those that are truly positive, right? And if you get it wrong, like if you say that it's a negative, then what you have is a false negative, right? So this term here is penalizing for the T2 errors, the false negatives. How does that work? So if this is 1, then if I'm doing my job right, then this value, my predicted value, is close to 1, right? And log of 1 is 0, so you don't get penalized. If I'm doing a poor job, then this value is close to 0, right? And so log of a number that's tiny is close to negative infinity, right? It drops. So this value, if you get this wrong, then this value becomes, it approaches negative infinity. It gets really big in the negative direction, right? Notice there's a negative sign here. So what this is doing, if you're going really big in the negative direction, negative, it makes that a really big number. So this is the error. This is the metric of the T2 error, right? Does that make sense? The second half of this equation here is for the opposite case, right? If the case was truly a negative, then this value is 0, and 1 minus 0 is 1. So we're going to count this. If it was truly a case, if it was a value of 1, then 1 minus 1 is 0, and you're not going to count this. So only considering those that are truly negative, but we assign them to be positive, right? So these are false positives. So this is going to penalize your T1 error. And the math works out the same way, right? So if this is 0, then this value needs to be close to 0 for this to be close to log of 1, which is 0, so you don't get penalized. And if you get it wrong, then this number grows. And you could visualize the dependence of log P on P, because that's what's happening here, right? So when P is when P is 1, meaning it's a case, then log P needs to be really log P is 0, and so asymptotically this approaches 0, and when you get it wrong, it approaches infinity, right? Negative log P, that's the negative. It approaches infinity, just like I said in words. So yeah, this is the definition of binary cross entropy. This P log P, that's like entropy. Okay, any questions? All right, so this is a balanced, this is like a balanced method, just like the ones before. This is going to be super important, so make sure that you actually get this down, right? Okay, let's move on to the next one. Okay, so far, all the error metrics that we've talked about have been for the binary case, right? So how do we handle multiple, when the outcome is has multiple classes, right? Multiple types of labels. Well, there are lots of ways, but to me, the most useful, the one that you're gonna get the most mileage out of is mutual information. Okay. So mutual information, besides also being able to use for continuous variables, so you should just always use mutual information. It measures how much information is shared between two things. Okay, so you have two variables, and we're asking how much information do they share in common. It's kind of like thinking about like how are they correlated, right? So in other words, how much information do I get from looking at how much information do I get on one variable by looking at the other? Okay, so what if those two variables that I'm considering are the actual and predicted labels, right? I can then say, imagine if your model is 100% accurate, then looking at the predicted label should tell you everything you need to know about the actual label, right? The mutual information is maximized. And the way to like calculate it is that you go by you loop through all the possible outcomes, right? 1 to n type of outcomes. And then you say, okay, what is the probability that the actual label was this case outcome, right? And the predicted label was also that same outcome, right? So what is the probability of all of my samples? What was the probability that happened, that they were both saying the same thing, the same label, all right? And then multiply that by that same value, the probability that they're in agreement, over the probability that that the actual outcome was that label. In other words, how many times does that label even show up, right? And in other words, how many patients, what is the prevalence, right? How many cases do I have versus controls, right? What is the rate of observing that outcome? Times the probability that the predictor would predict that outcome. Does this look, this should be ringing like bells to like people. This is oddly reminiscent of like Bayes' theorem, right? Which we won't get into, but what we have here is like the joint probability versus their individual probability, normalized by the individual probabilities. But moreover, look at the form. We have a probability P log P. It is at its heart an information metric. That's why they call it the mutual information. Okay, so so you just loop over all the outcomes. So it could handle multinomial classification, but for continuous variables, this sigma turns into you trade a Greek S for a German S, and then you have an integration sign, right? Integration over the limit of the range of values, right? So mutual information can be used for both continuous and multiple classes. And for our sake, just when we get into computer vision, this is related to what sometimes people call like the intersection over union. That's like the intersection is like where the joint probability, like where do both things happen at the same time, over the union, like the probabilities of either one happening. And sklearn, you'll read it as they call it the Jacquard distance. This is probably the deepest topic here, so please come at me with questions here. This mutual information, right? This sort of metric is at the heart of that AIC, the Akaki information criterion for feature selection that we mentioned last time, and also in those, in those stepwise selection methods, all they're doing is trying to maximize the mutual information between your predicted and actual values. Yeah. Okay, so with all of that out of the way, with all of that error metrics and how to like begin to like rate your classifier, let's actually talk about let's lead up to logistic regression, right? Like what function is it actually doing? At the heart is the logit function, okay? So in logistic regression, the output of logistic regression is a probability. What is the likelihood that you have a case, right, versus a control, right? What is the probability of that it's a positive, right? And so whatever your classifier, whatever this logistic regression classifier is, it better return a number between 0 and 1. And under the hood of what's happening is it's implementing a logit function, right? It's just the input divided by 1 less the input. You can tell that when the number is really big, then you have a big number divided over 1 minus a really big number is just that same number, right? So you got z over practically z. Negative z actually should be negative z. So that value is y. Does that make sense? This I messed up. This is actually should be a plus, I think. So yeah, big number divided by 1 plus a really big number is just another big number. So big number over big number is 1. When this is really tiny, right, actually like negative infinity, then you have a number divided by 1 over a really big number, right? So anything over a really big number is approaches 0. So that's how you get the range from 0 to 1. So you can see that it takes as input any real value number. So what if we wrap this? What if the input to this function, this z, what if that was the output of a linear regression? Yeah, so because linear regression just takes, it's like y equals mx plus b, right? It takes your features and weights them, makes some sort of weighted average, and returns a real number. And depending on those weights, that number can be anywhere from negative infinity to positive infinity. So you could think of logistic regression as sort of like a wrapper over linear regression. So how does that work? Oh, before we get into that, sorry. Before we get into that, the extension to that to multiple classes is what we call the softmax function. And the softmax is basically going to return a probability for each one of those classes, each one of the outcomes, and express it in a term of like e to the z, right? Like if z is like a negative number, e to the minus z, then you can see how this is a function that when z is 0, e to the 0 is 1, and when z is really big, e to the minus z is approaches 0. So this behaves like a probability, right? Going from 1 to 0. So you have a bunch of probabilities. Each k is the class, and you just need to normalize them, right? You just need to sum up over all the probabilities and divide by that number. So ensuring that the sum of probabilities is equal to 1, and now you've basically normalized your probabilities. It's called a softmax function. Really don't need to get too much further into that, but this is the extension to multiclass. All right, so logistic regression. Okay, so notice that we have a form of the logit function in here, and what the logistic regression is calculating is what is known as the log odds, right? It's the log of the likelihood that the actual label is 1 divided by the likelihood that the label is, not 1, right? 1 minus that. Does that make sense? So the odds ratio is this, and it has the form of a logit function, conveniently. So you can write this log of probabilities as a linear expansion, right? It's a linear expansion of coefficients weighting the individual features. This should look very familiar, right? This is basically linear regression, right? So this is saying that if I were to do linear regression, whatever that is, if I took whatever that is, that's equivalent to the log of the ratio of the cases being 1 versus the cases being 0. Does that make sense? The log of the odds is the definition of the linear regression. Okay, so you kind of can see now how this linear model is related to the logit, right? It's kind of like a wrapper for it. So what we're interested in is this. I don't care about the log of the ratios, right? I want the actual hazard ratio, right? What is the ratio that this, like, do I have the disease? What is the ratio of that? That's what I want to know, right? Well, conveniently, you just exponentiate the whole thing, right? E to e to all this, the log goes away, and you're just left with the odds ratio. And then e to all this, we can write as, imagine that z is that the output of your linear regression, right? It's just a weighted average. So e to the z, well, e to the z we can rewrite as 1 over 1 plus e to the z. This is the definition of the logit function. Does that make sense? So the logit function returns something, it will give you the odds ratio as the exponentiation of a linear function, right, of a linear model. So that's how you read the logistic regression, the output of the logistic regression. It's going to give you the coefficients to these variables. Okay. So how do we implement this? We'll walk through this in the notebook, but forgive the wall of text, but there's really is no other way that I can think of to do this. So in sklearn, I'll have you focus on some of these key parameters. These aren't all of them. This is just some of the key parameters. Okay, and let's begin with the solver. Okay, so you can by default it's this LBFGS. This is that linear model that I just talked about, right? That logistic regression, this form, that's this, and it works for binary classification. It's a default, right? But you can see how If you wanted to do a multi-class problem, then your choices are these Newton CG, SAG, SAGA, and LBFGS. And they'll handle a multinomial nominal loss. It's probably doing a softmax. So this is like where you start, right? What kind of problem do I have? And it's usually just going to be this. Okay, so the other important bit is this penalty function. Now, recall last lecture in feature selection when I talked about lasso, right? So lasso is a linear model that is employing what's known as an L1 regularization, okay? L1, recall that what that means is it's going to penalize those coefficients, those weights on the variables. It's going to penalize those that are big. The bigger you are, the harder it's going to try to pull you back down to zero, right? And if the feature is useful, then it'll continue, the weight will continue to grow. And so once it reaches the balance, the uninformative features are the ones that will, the L1 regularization is going to push those weights to zero, right? And that's how it does its feature selection. Okay, well, L2 is kind of like the kind of in that same spirit, but instead of just the size, the size of the weight, it actually goes as the weight squared. So what does that mean? So the penalty, instead of going to the power 1, it goes to the power 2. So when the weight gets really big, it really gets penalized, right? So it is a much stronger regularization term in that respect. However, when the weights get really small, it's hard to approach zero. In fact, it can't. Right? It's a parabola, and near the bottom of that curve, the slope, right? We were talking about how the slope is what you use to adjust the weight. That slope is zero, so there's very little pull on variables that are close with weights that are close to zero. So L1 will ensure that your variables their weights go to zero, and you can do feature selection. L2 is a way to wrangle in those weights that are blowing up really big, but it allows them to everything be important, right? And that can have its pluses and minuses, right? It gives you degrees of freedom for your model to move in. Well, elastic net is this idea of being able to go from one extreme, the L1 extreme, to the L2 extreme, right? It's basically going to have contributions from both, and you decide where I want to be all L1, 50% L1, L2, or all L2, something like that. And that so assigning the penalty to be elastic, you can then say here, what is that ratio? What is the L1 ratio, right? It's the mixing parameter. So if that value is 0, then it means you're in the full L1 regime. And if you let that be 1, then you're in the full L2. And in practice, you start somewhere in between, and you tune your model, you tune the training with some kind of grid search, right? Where like you try 0.1, and then 0.2, then 0.3, 0.4, and then, look for 1. So sklearn by default is going to do L2 regularization. Okay, and then C is the constant. Like, what is the strength of that term? The other important term that you can turn off, but I hardly ever do, is this fit intercept, right? So that's basically saying, are we going to allow the intercept to have some finite value, or are we going to force it that beta 0 coefficient to be 0, to be something more like correlation. So these methods, these algorithms are iterative type algorithms. They take steps, right? And you can impose a max number of iterations on here with this max iteration number here. So that means, hey, if by 100 steps you haven't converged, like your answer hasn't, if you haven't stopped learning, then cut the learning. Something's gone off, or maybe you'll never converge, right? This is good to keep your program from like running forever, you know. And multi-class, this is where you explicitly say what kind of regression am I doing, right? So usually just leave it on auto, and it's usually pretty smart if you're doing like multinomial or binary classification or even ordinal classification. But you can explicitly say set it. So your data could be multinomial, but you can your data can be binary, but you can enforce it to treat it with multinomial as if it was multinomial. It only has two classes, and it's probably going to use the mutual information metric instead of the binary cross entropy metric. So you could force it. And that's it. That's in a big mouthful. These are the big elements on how you implement the logistic regression in sklearn. Okay. So we're done with logistic regression. So let's focus now on the other half of classification. The other big one, well, random forest, right? Decision trees. So this slide is from last time. Just to recap, so what a decision tree does is it's going to take your entire data set, and it's going to consider splitting on your variables at a cutoff point, and it's going to try to maximize the disparity between those two groups that it split, right? And then if all the members of that split were all the same class, then your job's done. You've classified it. If it's still mixed, then do it over again, right? We talked about how we did that last time. So I also mentioned two big things. One, it's impractical to consider splitting every feature at every value every single time you want to do one of these splits, right? The problem becomes like computationally overwhelming, right? And the other thing is, like, I could keep splitting, right? And I can get it so that the subset here is just one, just one sample, right? And by definition, it's completely pure. It's all of the same class. So you could do this until every single one of these leaves, they call these leaves, right? Every one of these leaves has only one element, and you have 100% accuracy, right? So in that case, you're very much in an overfitting regime. And if you were to try to apply your tree on some new data, it's going to fail, right? So in practice, what you want to do is you want to limit the number of branches the tree is allowed to make. Yeah, and how to get over, instead of selecting every feature, you only select a subset of features. And because it's stochastic, now you need a whole forest of them, right, to consider all possible splits. And so that's how we get the random forest. So how does that look like in sklearn? All right. So your random forest classifier in sklearn has this number here, n estimators, that's the number of trees, right, you use. I think by default it's 100, but something like 500 is not uncommon, right? And it depends on how many features you have in your data set, right? If you have more features, but you're saying let's say that you have 100 features, and then for practical sake, you say, don't consider 100 features. At any given time, only consider 3 features. Well, then 100 choose 3 is like some astronomical number, right? Like and the number of estimators, that's you sampling that set, right? That big number. So you can see how the number of features is going to inform how many estimators you should plug into your random forest model. The criterion, that's the metric it's going to use to calculate disparity, right? So we talked about the Gini coefficient, right? It measures the difference between two groups relative to the difference within the groups. You want high similarity within groups and high disparity between groups. Well, we could use information, right? Like we could use like an entropy method, right? That says how much does knowing one variable tell me about the other, and minimize that, right? I want them to be disparate that way. Okay. Max depth. Sorry. Oops. Max depth is just how many branches, and the samples to split. Okay, so this is kind of important. So yeah, you know how I said you could keep splitting and splitting and splitting until eventually you have like one sample in each one of these leaves? Well, the split right before that had only 2 samples to consider. Do you see what I'm saying? So one way to impose a limit is just say like, hey, don't consider any split if you don't have anything less than 20 points to consider, right? That's what this minimum sample split number is. On the flip side, you could say on the number of leaves, say, I don't want you to ever make a leaf if it has less than 10 points in it. You know, so that's what this value is here. And remember how I said that you can pick how many features it's going to consider at every split? Like, you know, don't consider all the variables, just consider 3 at a time, right? You set that with max features. So auto, I think, is the same thing as square root. So it's going to say consider only the square root of the number of features I have. So if I have 100 features, only consider 10. And log 2 is just like it sounds. Take the log 2 number of features. Bootstrap. So this is really useful. So Bootstrap, remember from 2 lectures ago now? So a Bootstrap method means that you're going to resample. If you have 100 samples, you're going to resample 100 of them with replacement, right? So some samples get sampled twice, some don't get sampled at all, and you can make many realizations of these resamplings with replacement with the Bootstrap method. Well, that's what the Bootstrap method is. So if you say true, it's going to say sample with replacement, basically, and make multiple copies. And max samples is just that. How many of these Bootstrap samples, right? Do that 100 times. Or you could set it as a fraction, right? I want you to sample, 20% of my data, 20% of my observations. And that's it. That's how you implement random forest and logistic regression. So this is a great place for questions because this is actually the end of the theory part. Do we have any questions? Chat open. Okay, so this is probably a good place to jump into the notebook. Okay, so let's jump right into the notebook. the launch your Jupyter notebook, and where do I have it? I have it on the desktop, don't I? There it is. Oops. Module 7, the notebook. Okay, so for the notebook, what we're going to do is we're going to go through the homework. So we're going to kill two birds with one stone. We're going to go through the homework from module 6. We're going to look at the PIMA data set, do some of that feature selection, and then we're going to implement the logistic regression and a tree-based model. If we have time, I'll try to do maybe lasso or an elastic net to show how we can do the to explore regularization. So let's talk about the PIMA data set. So just to recap for everyone, right? The data set is in that data folder, and there's a data description in it. It'll basically say this, right? So we have 8 features and the class that we're predicting. Those 8 features are the number of times the patient was pregnant. These are all female Native Americans. Their blood glucose. After an OGT, an oral glucose tolerance test. Their diastolic blood pressure. The thickness of their tricep skin fold. The blood insulin, the body mass index, like family history, basically, of diabetes, their age, and then whether or not they have diabetes. 1 for diabetes, 0 for no. I just realized I don't have my chat box up. Okay, so we could just load up all the requirements here. And the first hack was to load the data. Okay, so to load the data, I'm going to have to change this because it's not here anymore, is it? It's on the desktop. Python, and I think it's called name, because I'm looking at it right here. So yeah, find where your data is. It's in module 7 data. And the first problem we had was that if you looked at the data file, it's just numbers, right? It's just numbers. So these columns, those are the features, and I mean, there's no header, right? You're going to have to make that your own. This is part of formatting, right? It's partially unstructured data. Each row, those are the patients, right? And we have quite a bit. I think I could just click here. How many? Like 770 patients. Okay, so the first thing we need to do is make those headers. So to do that, I assign the column names. You can just do it like this, df. So we read in the CSV into this data frame called df, and then we assign the columns, right? So this is the number of times pregnant. You just read this, right? Number of times pregnant, the blood glucose, diastolic blood pressure, diastolic blood pressure, the skin thickness, the blood insulin, BMI, family history, age, and then this is the diagnosis of diabetes. And then we're going to generate the table 1. The thing that we needed to do here was define how we group them, and we group it by the last feature, which is the label, right? So this was the first problem. And here we go. So what do we see? Okay, well, pregnancy, the number of times pregnant is correlated with the outcome, very much so. Blood glucose, unsurprisingly, is correlated with diabetes. Your blood pressure, I mean, I guess you could say it doesn't reach significance. I mean, that's its p-value. And the skin thickness is, you know, just slightly above significance. Insulin, yeah, I no surprise. The blood insulin is correlated with diabetes. BMI, you know, that's no surprise there. Family history, no surprise there. And your age, right? The older you are, the more likely you are to get diabetes. So it looks like pretty much, if I was to do a filter method, I would probably only throw out diastolic blood pressure if I was doing a filter method. And maybe even skin thickness, but everything else seems to be very well, much correlated with the outcome. Did anybody have any problems with this part of the homework? Everyone got to this point? Okay. So the other thing to look at when you get to this point is you look at these warnings. So this dip test is going to tell us if there's anything looks like it's multimodal, right? And it's saying quite a few. It says the blood pressure, age, blood insulins, pregnant, and skin thickness seems to be multimodal. I'm not going to focus on normality because we kind of can see that with our own eyes. And I'm not going to look at outliers because we have so few. So let's look at this multimodal. Okay, so yeah, that's what I say here. Let's address the wording. And so what we're going to do is plot the feature distributions. So so what we're going to do is we're going to loop over the columns in that data frame, right? Pull out those features and then drop any NAs and plot the kernel distribution function, right? And do that for every feature. Okay, so what do you see here? How would you interpret this number of pregnant times? What feel free to chime in, like. Would you be comfortable using this feature in a okay, so yeah, some might say there's a tail here, right? It's not an extreme tail. Some might say it's a tail. So how would you like tuck in that tail? This is a question too. Everyone in the audience.
The log transform.
Yeah, you'd log transform it. What would happen if I log transform this?
The ratios would stay the same, the ratios between any two data points, but the absolute differences between them would shrink. The bigger the absolute differences, the more it would shrink.
In a perfect world, yes, but you won't see that. Why won't you see that?
That I don't know.
So some people have never been pregnant.
Oh yeah, the zeros will
break it. The zeros will break it. Yeah. So you gotta like whenever like you see a tail, like, oh, I'm gonna log transform it. It's like, oh wait, first check, does it cross the zero line? If it doesn't, you're gonna have problems. So it's not too bad. I would probably leave that alone, right? Blood glucose. What is the problem with blood glucose? I think I already said this earlier.
Some people are dead. They have
some people are dead. Yeah, some people are dead. These, if I saw this, I would say that can't be, these must be missing. This is how they probably are coding missing values, which is a terrible way to do it. So these are the ones that you'd have to impute. You can make some argument that maybe there's another mode here, but it's such a soft shoulder. I'd be happy with this curve. So this needs to be addressed. Okay, diastolic blood pressure. Yeah, some people are dead. Right? They have no blood pressure. This needs to be fixed. These are missing. Otherwise, the curve is quite nice. Okay, skin thickness. What do you guys see here?
Well, same, there's zeros again. A lot of thin-skinned people.
Yeah, there's zeros, yeah. So that's the bigger problem, right? At first glance, like when I would see something like this, like two humps, I would say, oh, this is multimodal. I should actually make this into like a binary variable. It's either this or that, especially since their peak heights are so similar. But yeah, it doesn't make sense for your skin thickness to be 0. It has to be something, right? So this is probably missing data. And if there's so much missing data here, this might be a candidate for, we'll see how imputation will fix this, but this might be a candidate to drop. The filter method, using the filter method suggested that skin thickness is not that great, but that's probably because it's contaminated with all those zeros. So, I guess using those 2 bits of evidence, I would be in favor of imputing these 2, but I would first have to count how many of these missing values am I talking about. If it's like less than 20%, then I'm good. If we're imputing like half the data now, I don't know if, you know, we could start imputing that. Okay, blood insulin. I can't tell if there's zeros. If there are, man, this is a terrible variable. Like maybe the real data only starts here. And BMI, again, these are missing data. Otherwise, a good curve. These definitely impute. This, I don't know, man. This you might even throw out. I don't know. Family history. So this wasn't a yes or no question. It was like an index. And I don't think they cross a 0. I don't think there's any 0. So this might be a good candidate for log transforming, but you know what? Like it's already from 0. Like it isn't like increasing by orders of magnitude. So I would probably leave this one as is. Age, there seems to be modes. So you can either be young or old or very old. But maybe you could tuck that tail in. I don't know. Especially since it doesn't cross 0. Usually, I should make a note. Usually we don't log transform age because age isn't one of those things that increases exponentially, right? The lifespan is pretty much fixed and people age year to year, right? You don't age 2 years and then 4 years and 8 years. So if it was something like a concentration, like the level of blood insulin, that could increase by orders of magnitude. Those are good candidates for log transform. Age, I don't feel very comfortable ever log transforming it. And DB, well, we know that it's the categorical variable. So that's how I would have treated that missing data. Did that make sense to most everyone? Yeah, like, and this is how you do it. You look at the distributions and you march along, and you start making your notes of like, oh, I think I'm going to treat it like this, and treat it like this, and treat it like this. So, so what we need to do is treat the missing values with a mean, tuck any long tails. You could use a log 2 transform, and we need to partition our data. Once we're done cleaning our data, first thing you do is you partition it, okay? So impute any missing values with their column mean. So this is the this is the naive way to do it, right? I could tell that this did nothing because there are no missing values, right? So how would you guys rewrite this?
You can use the replace method instead of the fill in a method.
In this data, missing value is 0. Yeah, this is what we kind of concluded. So the documentation that came with the data didn't say that. We had to infer it based on what we knew, right? We had to infer that the zeros were missing. So yeah, you could do the replace, but you're gonna have a problem if you did it across the board, right? Some things need to be 0.
Oh, yeah, but the value parameter of the replace method takes
Like you define you have to
it takes a
define
dictionary like. So basically, if you just say df.mean, or yeah, df.mean, or but not df.mean, but df brackets columns.mean, and you define your columns as the thing that you want.
Yeah.
So calls is whatever 5 columns you're interested in. And if you pass that df columns.mean to the value argument, it'll skip the columns that are not in your values dictionary or series in this case.
Yeah. So you're saying basically take this and put it in, I'm going to comment this out. I'm going to just copy, comment that out, and then df columns mean, put that here.
I put it in chat.
Oh. Plasma glucose, so calls. Here, I'll write it here instead of reading the. So we're saying columns is plasma glucose, diastolic pressure, triceps, serum insulin, BMI. Plasma glucose, yes. Diastolic blood pressure, yes. Triceps, skin thickness, yes. Serum insulin, yes, but a big if. And BMI, yeah, absolutely. So what did I call it? I call it blood glucose, didn't I? Blood glucose, blood pressure. I think I just called it skin thickness. Let me double check before I get an error. Skin thickness, yeah. And I think I said blood insulin and BMI. BMI, blood insulin, yeah. Okay.
You have BMI in caps. Yeah.
Oh, did I caps it? Yeah. Okay, and then replace. So df replace, to replace the zeros with the values of the means of these columns alone and do it in place. So I don't have to say df equals this. So does that make sense to everyone? Let's just see if I didn't bring it. Yeah, looks like it worked. So I can just rerun this to plot the distributions again. This should work, right? Pregnancy, blood glucose, perfect. That looks great. Diastolic blood pressure looks great. Skin thickness. Yeah, this looks more normal, doesn't it? Some people are just the normal skin thickness and then varying levels of skin thickness. Blood insulin, that looks normal. This might be a candidate for log transforming now, because this is quite a long tail that goes orders of magnitude big. So I'll make a note of that. Blood insulin. Okay, BMI, that looks great. That's fine. Family history, it has a tail, but it doesn't go orders of magnitude, so I'm gonna leave it. And the mantra is the less you massage them, the better, right? Age, I don't do anything to usually. Okay. So now we're gonna log transform, and we said not age, but blood insulin. Okay, and then we're just gonna do MP log. I could log to it. Div columns. Okay. And it did something. We could just plot this again to see if it worked. And blood insulin. Yeah, it tucked in the tail. You see how it's now not orders of magnitude different? So this is fine. This is fine. I think everything is fine now. We can partition the data now. Okay, so to partition the data, I don't know if we ever covered this. I was hoping people would just Google it, but you could just sample, right? I could sample a fraction of the data. I'm going to sample from DF 30% of it. And that's going to be test. And then I'm going to then make a training set and drop from the DF, everything that's in the testing set, drop it from DF, and that's going to be my train. Does that make sense? That should be straightforward. And I'm displaying here like the shape of my data. So there should always be 9 features, right? Eight predictors in the class. And my training set is 500 and the other one's about 200. So that looks about right. Okay. Now that we've sort of cleaned the data and partitioned it, we can regenerate this table 1 just to see if, I'm curious to see if like skin thickness in particular now reaches significance. So I'm just gonna do this. I'm gonna cut this and put it here. And this is what you would do after you've done cleaning your data and you partitioned it. It's a nice thing to test. Here, let me do this before I answer the question. The question is, can we use test train split? Absolutely, you can do whatever you want, whatever gets the job done. I think in this, we use test train split here. Okay, so what I'm noticing here is that actually this is going to generate a different. You didn't put in the seed. Oh, I didn't. I didn't put in the random seed, so it's going to be different every time. And maybe you don't want that. Every time you run this notebook, you want it to reproduce the exact same data. You should put in the seed like we did with the test train test split. I won't look at the syntax right now, but I think everyone gets what I mean there. Okay, so I just cut and pasted the table 1, and this is where I want to like just check that now everything is well behaved, right, or as best behaved as I'm willing to get it. Okay, so look at that. Everything is significant now. This is a really good sign. These are toy problems, so I'm not surprised. You would never see this. Something's always going to be uninformative. But that was kind of like the big challenge of the homework problem, right? Was to do some not insignificant formatting, like data cleaning. And the only way to do it is you can't do it how do you call it? Like automatedly, like, oh, I'm just going to put in this magic function, it's going to do it. We had to look at the data, especially when it came to those zeros. And I led you astray, like I purposely led you astray with that fill in A, because that's the way we had it before. Like, this will work, but it's not going to give you, the right data processing. So this is great, and I'm not going to worry about these because I have no good reason to get rid of outliers from what I saw. And the normality, I mean, it's never going to be perfectly normal, and it looked fine to me. So you can hark on, you could do this forever and ever and ever. We're just going to call it here. Okay. So here we needed to compare models. So maybe I should stop right here. Any questions so far on what we've done? This is the first big step, was the data cleaning. All right then. Okay, so compare models, right? So the first problem was here. Okay, so this function is going to compare selected features. You pass it a data set and some selected features, and it's going to make two models, right? A prodigious model that uses all the features, and a parsimonious model, and then compute and then score them, right? So here we need to define the predictors. So let you guys fill in here in the chat. What do you think should go in here? It's pretty simple. Whatever we named our last column. Yeah, exactly. Great. And this one is, well, by definition, DB. Yeah. Okay, so then we're going to select the indices of those features for feature in select features. If feature is in X, where X is our data, right? So this is going to give us the indices of those selected features, and we're going to do a 70-30 split. So I think I mentioned this last time, but this split here is independent of the big partitioning that you did yourself, right? This is just internal to this function. It's gonna, you give it some data, and its first thing it's gonna do is split it so that it can, what it's gonna do is going to score the model on the test data and train on the training, right? There's actually nothing to do here. This is straight out of the lecture last time. The parsimonious and prodigious models are both linear regression models. On a side note, is there any reason why it's a capital X but a lowercase y? It drove me nuts, dude. Yeah, it's convention. I actually have that's the way I learned it too. So I just do it that way, and it's because of that. Yeah, when I was first starting off. There you go. Matrices and vectors. Yeah. Yeah, well, I was like, well, is it a capital X? Is it a capital Y? And now I just do it automatically, so I guess it's muscle memory and it works. Yeah, I easily recognize that error when I say, because you see it all the time. So you're part of the club now. Yeah. Yeah, I still hate it. Yeah. Well, I suppose if, you know what though, I actually didn't know that. It makes sense too. And when I have multiple outcomes, right? Then I guess that should be a capital Y, because I have a matrix then, right? It's number of samples by number of outcomes. If your model spits out not one outcome, but 2 or 3 outcomes, then I guess Y should be a capital, and then break all of my codes. Okay, thanks. Yeah, and then we're outputting the score. So the score here is accuracy, right? And remember what I said, accuracy is actually a terrible score if the labels are imbalanced. So, but we know that they're pretty balanced. 2 to 1, it's good enough. It's good enough. We could try F1 score. Why don't we do that? So I would look it up. I would say, what is it? Linear regression. So I say SK learn linear regression F1 score. Oh, it's just called metrics F1 score. That's easy. Okay, sklearn metrics F1 score. Wait. Metrics F1 score. So I guess it's going to be, we passed the model, don't we? I'm sorry, guys. Oh, you just passed it the true and the prediction, and it does it for you. Okay, okay, we could do that. So we're going to here sklearn metrics. What do I have sklearn as? How did I install it? Oh, I don't have it by itself, so I need to do metrics. Yeah, okay, so from sklearn metrics import, what is it called? F1 underscore score, F1 underscore score. F1 underscore score. And then we just call it F1 underscore score. Print out the score, and it's going to be, I should like copy and paste it instead of going back. The true and the predicted. Okay. Y true is just lowercase y, and the predicted are, I have to do predict, don't I? Yep. I think it's going to be called prodigious model predict. Oh, it's Y test for your true. Yes, you're right. Because I'm testing, they're reporting the errors, yeah. Y test, prodigious model predict, and I'm going to have to look this one up too. All right. sklearn linear regression predict. It should be logistic group. The method, here it is, just predict. Yeah, predict on X. Okay, that's what I thought it was. Prediction mode predict Y, predict on X. Test. Right, does that look good to everyone? I think that looks good. Train, it's for trues, X train. Why X train?
Never mind.
Oh,
My mistake. You're right.
it should be test. Yeah.
Yeah, sorry.
So yeah, we fit the model with the training data, and now we're predicting on the testing data. That looks right. Am I missing one of these? Yeah. Okay, so that looks about right. We'll see if it breaks. We'll see if it breaks. And then for this one, it's just going to be the parsimonious model, huh? Oops. Oh, good. But there's going to be parse model, isn't it? Parse model. Okay. Run. Okay, so the filter method, select features is just going to be everything. So let's just skip this because we don't need to, we know the filter method is going to select everything. Baruda. Okay. Sorry, was there a question? No. Okay. All right. So for Baruda, is that a question? Yeah. No. Okay. MP rate drop. Oh, it's just like before, right? let's drop the label. And we're going to, for Y, we're going to take that one. Okay, so random forest classifier, number of jobs, -1. So let's limit the max depth. I think this is way too many depth. So remember how I said the depth depends on how many features? We're talking about 8 features here. So man, something like 2 or 3 is probably what's in order here. So let's just limit it to 3. I want to say 2, but let's just limit it to 3. And number of jobs, if I remember correctly, number of jobs is 4.
I had a question here.
Go ahead.
Actually, number of jobs -1 just uses all cores, so you can leave it at that. But when you define your X and Y,
yeah.
Where you use like df drop, shouldn't it be df train? Because right now you're using the entire data set to select features on.
You're absolutely right.
Okay, I just want to make sure that I understood that right.
Yep.
Thanks.
This df train is not, so when I originally wrote it, df, like the first thing I did was I would take the test data, save it, and then drop stuff from the data frame, but in place. And that's why df was going to be always my training data, and df test was going to be the testing. Did that only because in here we use this test underscore and train underscore, and it was getting a little confusing, but that's the way we've defined it. So train, correct. Random forest classifiers, weight, balance. This should work. The feature selector. Okay. So for this, we have to look back at how we did the feature selector. Did anybody get to this part?
Yeah, it's a Baruda Pi.
Yeah, Baruda Pi. It was in the oh, there we go. Let's use Lichu's answer here. Baruda Pi. The estimator is a forest. Is this estimator? Number of estimators is automatic. Great. We're both 0, so it doesn't spit out everything. And the seed is the seed that we have up here. Did we call it seed? I'm gonna assume yes, because that sounds about right. Okay, and then the feature selector is this, and this is just to spit out the rankings. Feature 0, 1, 2, 3. This should work. This should work. Then it didn't work. Oh, there's a error code missing somewhere. Ah, here. Drop DB, right? Yeah. The features are everything but the label. So DB. Yeah. Sounds about right. So never mind the errors. What happened here? No, these are actually like errors. What's going on here? Oh, it's still running. Good. Whew. Great. And guess what? It kept everything. 1, 2, 3, 4, 5, 6, 7, 8. It kept everything because everything is informative. Well, great. There's not much feature selection going on here then. Okay. Should we try to do the lasso in the next 3 minutes? I think maybe here, I will, since we're really close to the 50-minute mark, here I'll open up for questions. We can have an open discussion. I hope that you caught the the heart of what the homework was all about. It was about actually applying the skills you learned about data processing, and you follow the steps for feature selection, and it looks like nothing's going to be, like the feature selection problem actually becomes a trivial problem, right? When we get back next time, we'll attempt an elastic net. Yeah, because we just did because we just did a tree-based method now. So any questions from anybody, please feel free to ask. For homework, I guess I take it that a lot of people got stuck and didn't finish, so you can attempt this other part of the previous homework assignment. You can even apply the methods from this lecture to that, and then try to make a final logistic regression model on the training data. Yeah. Okay, then I'll stop here then, and I'll go back to Henry here. Still around. Who wants to say any send off?
Sure. Did you want to go through the classification example?
Well, I actually have to leave it at 6:50. So
Sure.
yeah.
Okay.
We'll pick it up next time when we talk about regression.
Okay, sounds good. All right, well, thank you so much, everyone, and look forward to seeing you all next week then. All right. Have a good rest of your week.